Hi class. In this section we are going to use all of the things we just learned in the previous two sections to solve applications of systems of equations. So generally systems of equations represent some sort of physical phenomenon, some situation where you have multiple things that can change, and you need multiple equations to represent the entire system. Okay, so for our first example, what we're going to do is we're going to try to find the equilibrium temperatures of different heavy wires that have constant temperatures at their endpoints. Okay, so what's going to happen here, if we look at this picture, is that our wires are here, okay, and they are connected at what we like to call nodes. The endpoints of the wires are held at a constant temperature. This temperature is 30 degrees. This temperature is 40. This is 70, and it's held constant. It doesn't change. It does not fluctuate. So as the heat travels through the wire, obviously at different points along the wire, there's going to be different temperatures. This is hotter than this one. This is hotter than this one, but less than this one. So as the heat flows along the wires, you're going to have different temperatures depending on how the temperatures are, or how the wires are connected. Okay, so what we're going to do is we are going to assume that the temperature at any single node is the average value of the temperature of the two nodes that connect it. Okay, now generally this is not true, obviously, because from this picture it looks like the node x1 is closer to this endpoint than it is to its adjoining node, but for all intents and purposes we can assume that it's pretty much the average, right? So this is our assumption. If we wanted to know the exact value, that would be a partial differential equations sort of course. We're talking about heat flow through a rod or a wire, which we're not doing in this class. Okay, so here each node has a value approximately equal to the average value of each connecting node, right? That's a good enough approximation for us for this case, for what we want to do right now. Okay, so that means that x1 is equal to the average value of 30 plus x2 plus the value at x3, right? So this plus this plus this divided by 3. This is a higher level course. We don't really talk about division anymore. Okay, division, all division is a reciprocal multiplication. So you will not hear me say divide in this class. You're going to hear me say multiply by 1/3. Okay, it's the same thing. Obviously, you guys are linear algebra, you know that. But we tend to, in the higher level courses, talk about division as a form of multiplication. We will not say I'm going to take these and divide them by 3. We're going to say I'm going to add the sum of this and multiply it by, multiply it by 1/3. Okay, so that's what I'm going to do. I'm going to take the average of this by adding them together and multiplying by this reciprocal value. Okay, same thing for x2. I'm going to add this plus this value and divide by the total, or multiply by 1/3. Okay, let's come back to this. So that's my value for x2. Okay, so if you notice here, what I skipped over briefly is I took this equation that we had, okay, and I turned it into the general form that we have for a linear equation, where the constant value is on the right hand side and all of the variables are on the left hand side. So what do? Multiply by 3 gives me 3x1, and then I can subtract x2, subtract x3, and that leaves me with 30 on the right hand side and all of my variables on the other side. So we're going to do that for each of these. Okay, I'm going to solve for x2. x2 is the average value of the nodes and the end wire connecting it, surrounding it, I should say. And then I'm going to turn this into equation by multiplying it by 3 and subtracting x3 and also subtracting x1. Okay. My x3 node should have a temperature of the nodes connecting it as well, 40, x2, and x1, multiplied by 1/3. Same thing, clear the fraction out and isolate the constant value on the right hand side. Okay, so this is my system of equations that represents this system. Okay, each x1, x2, and x3 has a single value that it will have according to these constant temperatures at the endpoints of the wire. Right? So if I want to turn this into a matrix, okay, again, I'm just pulling out the coefficients. Right? So I have 3 along, what's this called again? Do you remember? Our main diagonal. Okay, and it turns out that everything else is -1s, and then I have my right hand side separated by these dashes. Okay, so now that we've formed some equations and we've turned it into a matrix, I can now solve this system by using our Gauss-Jordan elimination, which is what we're going to do. Okay, actually for this example, so some of these examples I'm going to actually go through the calculations, and some of them I'm going to just say, hey, do it on your own, but this is the end result. Okay, so for this one we're going to actually work through everything. So again, remember there's multiple ways to start this. The one thing that I do not want to do is take this row and divide everything by 3 to get a 1 here. That is a terrible, terrible way to start, because then I'm going to have fractions here, and as I go through my work, I'm going to have fractions everywhere. I really don't want to do that. So let's swap some rows. Okay, I could have swapped with R2 instead of R3, but it's arbitrary. Okay, so here I'm going to swap with R3. So these 2 rows swapped out. Okay, next thing, so again, remember, I'm kind of trying to do one thing at a time. So the next thing I'm going to do is I'm going to multiply all of this by -1. Okay, so that I have a 1 here. And now I want to get zeros below. So I'm going to do something a little different, because I'm assuming you guys have experience now that we're on the 3rd section. We've covered quite a few examples, and you should have done some homework and things like that. So I'm still going to do one at a time, but I'm going to do 2 things. Okay, I am going to clear out this entry by turning R2 into R2 plus R1, and then I'm going to clear out this entry by making R3 equal to R3 minus 3 times this one. Okay, so I'm sure you already knew that, but instead of doing that in 2 separate steps, I can do that all at once, because I'm changing this row with R1 and I'm changing this row with R1. I am not changing this row and then trying to change this row by using this row. Okay, so I'm using just one fixed row to do 2 things. So I can do that at the same time. Okay, that's okay. But what you don't want to do is, let's say, swap rows and multiply by negative at the same time. Or do swap rows, multiply by negative, and then a multiple of another added to another row at the same time. You don't want to do too many things, because then you're going to have mistakes. Okay, but what you can do is, if you notice, R2 is only being affected by R1. R3 here is only being affected by R1. I'm not taking R3 and doing something with my old R2 or my new R2 in this single step. I'm just using this one thing, this one row, to manipulate 2 other rows. So that way these 2 rows have no relationship to each other. They're only being affected by this one row that is staying fixed in this iteration. Okay, so that's okay to do. If you're not comfortable with that, then don't do it. Okay, if you've been having success with whatever you've been doing before, then that's fine. But you can do kind of 2 things or 3 things. If I had 4 rows here and I had to do another, I could have added another step also. If I'm using this first row to manipulate a fourth row here. I could have added something else here. Okay. But the point is that I'm not using this one to affect this one as I'm changing R2, right? R2 and R3 are not being used together as they are being manipulated. I'm just, I'm using one fixed row to manipulate two others. Okay. So, what do I have? I'm going to have zeros under. These values are going to change as well. Okay. And so now I can move on to the next phase of my Gauss-Jordan elimination. My goal is to eliminate this one. Now I could also just add these two together to get this row to zero out, which is fine because my goal is to make this zero. I'm going a little bit backwards, but that's fine because then I'm going to make this one. But for what we're doing right now, I'm going to stay with the algorithm. I'm going to turn this into a 1, and then I'm going to manipulate this one. Okay. So I'm going to divide both of these by 4. Now that's not the greatest thing to do because I'm introducing fractions here. But I really don't have a choice because these two values are even. There's nothing else for me to do to make this 1 besides divided by 4. Now I could have zeroed this out first, which I didn't do, but that's fine. But I can divide everything by 4. I really don't have a choice but to introduce fractions here. So I have to, okay? And that's fine. So I have 1, negative 1. This is 15 divided by 2. Negative 1, 2. 75 over 2. The nice thing is that both of these have a common denominator. So when I add them together, it's actually pretty easy to add these together, which is the next step, right? If I want this to be 0, I add them. So this will be 0. This will be 1. 75 plus 15 gives me 90, right? And 90 divided by 2 is 45. So I still get a whole number. I could have done the same thing here, and that's okay. Okay. So now I'm done with the forward phase. I'm done with the Gaussian elimination. Now I want to start with the Gauss-Jordan elimination, which is the backwards phase. So I'm going to make this 0, make this 0, and then work my way up to this one. So I can do two things right now. I can make R2 equal to R2 plus R3, and I can make R1 equal to R1 plus 3 times R3. So I'm using this one row to zero out the entries above it. Okay. So that's what I have here. I'm adding these two together, and I'm adding this one plus 3 times this one to zero it out. So this is what we have so far, and I'm almost done. I need one more, so I'm going to use these two together. So R1 will turn into R1 minus R2, okay, in order to eliminate this. And so then I just figure out this math, right? So 95 minus 105 over 2. So I just make my common denominators, yada, 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 and I am done, right? I have ones along the main diagonal, zeros everywhere else. I have my values. That means the value of x1 is 85 over 2 degrees, x2 is 105 over 2 degrees, and x3 is 45 degrees, right? x1, x2, and x3. Okay. So that means that this is our solution. Generally, this is the answer that I want. Okay. However, and so when I say that, I mean fractions. Okay. I generally want fractions. If you give me things that are non-fractional answers, I will take off values. Okay. I will subtract points. However, the exception is when you have an application problem. If you have an application problem, these answers don't make sense because people are not used to these answers. Okay? So for something like this, I want you to bring it down to its decimal form. Okay? Now, you might be saying, Professor Williams, what the hell? Why can't I just write this in this decimal form? Maybe if I'm using a calculator, that's what my calculator gives me, right? I don't care what your calculator gives you. I want a fraction. A fraction is an exact answer. A decimal is an approximation. In this case, your fractional value and your decimal value are equivalent. They are exactly the same. However, if this was 85 over 3, you would then have to write some value that is a decimal approximation, because you would have to cut off after 2 decimal places, 3 decimal places, 4 decimal places. You're going to lose some information. Whereas 85 over 3, I know exactly what the value is. Okay? In math, math class especially, we want exact values. In engineering, physics, chemistry, what have you, a decimal approximation is fine, because you don't need all of those points of exactness, I guess, right? Approximate values are generally pretty decent. You have to take into account rounding error and things like that. In math, we don't do that. We want exact values. So I generally want the fractional values. Okay, I will take points off on things if I don't have your fractional values. Again, the exception is application problems. Application problems should have an answer that is easy to digest for the reader, period. And that's why engineering, physics, chemistry, etc., decimal approximations are okay, because it's easier for the reader. You're using it to be able to do something. In math, we don't care about that. We want exact values. Okay? So just a heads up for later on in this class, or if you ever take any other class with me, right? So let's do another example. So for this example, we are going to balance a chemical equation. Okay? So now we're moving on to the chemistry side of things, possibly physics course. Might talk about balancing chemical equations. So our chemical equation is that we have a potassium superoxide and a carbon dioxide, and we are changing it into K2CO3 and O2, a covalent oxygen molecule. So if you notice, if you're familiar with these things, there are generally numbers on the outside saying I have this many molecules of this plus this many molecules of this in a reaction will give this many molecules of this plus this many molecules of that. Okay, so we don't have the molecule values. That's what we want to figure out. How many molecules of each do we need for this thing to make sense? Okay, these subscripts tell us in each molecule how many atoms there are of each one, right? So in this potassium superoxide, there is 1 potassium and there are 2 oxygens. Okay, that's what this molecule looks like. It's 1 potassium atom plus 2 oxygen atoms combined together. Carbon dioxide is 1 carbon atom with 2 oxygen atoms attached. Okay, so if you notice, this doesn't make sense, because if I were to just add these, if I had 1 of these plus 1 of these, it wouldn't make sense, because there's only 1 potassium, but here there's 2 potassiums, right? If I put 2 of these, then that means there's 2 potassiums now, but there's 4 plus 2 more oxygens, and here I have 5 oxygens, right? So I need to pick the values that make this chemical equation balance. Okay, so I think I did a pretty good job of explaining that. I have a big old long write-up here that explains that, so let's just kind of go through this. So in 1 molecule of potassium superoxide, right, that's this one, there is 1 atom of potassium, the K, and 2 atoms of oxygen, as I just said. So we want to know how many molecules of the oxidizer, that's this thing, the potassium superoxide, and how many molecules of carbon dioxide to result in potassium carbonate, that's this thing, and covalent oxygen, right? So it's 2 oxygens basically sharing an electron, so covalent oxygen. the number of atoms will not change in the chemical reaction. So if we had 3 potassium superoxides and 1 carbon dioxide as our reactants, the things that we're using, okay, so reactants and products, we should have 3 atoms of potassium, which we don't, and 1 atom of carbon, which we do, and 8 atoms of oxygen, which we do not. Okay, that's if there was 3 here, because we have 3, so we have 3 times 2 is 6, plus 2 more would be 8, and there's 5 here, and there's only 2 here. Okay, so we got to, again, this is just a completely different example of how many of each atom, or I'm sorry, how many of each molecule do we need to make this make sense. Okay, so let's rewrite this equation where we have variables for the unknown amounts, right? So right now there's no constant coefficients, I should say, right? So if I replace them with x1, x2, x3, and x4 to say, hey, I need this many of this and this many of that in order to have this many of this and this many of that and be balanced, okay? What we're going to do now is we're going to just write equations for, not for each x1 and x2, but for each K, for each oxygen and each carbon, okay? So for potassium, on this side, on the reactant side of the equation, I have x1 of them. On the resultant side, right, on the product side, I have 2 times x3, right? So for every one of these molecules, there's 2 potassiums. So x3 times 2 is how many potassiums are on the product side, on the resultant side of the equation, or the reaction, I should say. For oxygen, it's the same thing. So there's going to be 2 times x1 oxygens plus 2 times x2 oxygens from the carbon dioxide. And then I'm going to have 3 times x3 from the potassium carbonate. And I'm going to have 2 times x4 from the covalent oxygen. So for carbon, I'm going to have just x2 of them over here on this side of the equation. And I'm going to have x3 of them over here on the resultant side. Okay. So I can now put these into equations by moving everything over to one side of the equation and having my constant values on the right hand side, okay, which are zeros, right? So now I have a system of equations where 0 is on the right side, and then I have all of my variables on the left side. So this is my system. I'm going to take this and I'm going to turn it into a matrix. 1, 0, negative 2, 0, 2, 2, negative 3, negative 2, 0, 1, negative 1, 0. Okay, so that's what we'll have for my augmented matrix, plus this column of zeros with the dashes on the right hand side as such. Okay, and then the way that we want to solve this is the same thing. So we know that there's a 0 here. I can get rid of this row by going R2 becomes R2 minus 2 times R1, and we can go down the line. Now if you notice, I have 3 equations, 4 variables. Okay, when I reduce this down, even if I put this into echelon form, I'm going to have a free variable here, right? The only way to not have a free variable here is if all of these turn into zeros, and then that means x4 would just have to be 0, right? Actually, I think it still means that it would be free, right? So no matter what, there's a free variable here, because I don't have enough equations to solve for all of the variables that I have, okay? So we're going to go ahead and just look at what this looks like in its reduced row echelon form. So remember, that's when it's zeros below all of the pivots and zeros above all of the pivots, wherever it is that the pivots end up being, right? It does not necessarily mean that it's always here, here, and here. It's very easy that the first one is here, the next one is here, and then the last one is here, okay? So let's see what we got. So they are in the very first positions. Then as you can see, I am not able to get rid of the x4 column of coefficients because I don't have enough equations, right? So I do have a free variable here. My free variable is x4, okay? x4 is a free variable. That means that x3 is, so remember, this is the equal sign. I have a 2/3 times x4, right? All of these are multiplied by x4, all of these by x3, by x2, by x1. So that means this equation here is x3 minus 2/3 x4 is 0. So when I put this into my form, when I want to know what x3 is, it is, I move this over, positive 2/3 x4. x2 is positive 2/3 x4. x1 is positive 4/3 x4. Don't forget to bring this over to the other side, okay? x1 is 4/3 x4, x2 is 2/3 x4, and x3 is 2/3 x4. x4, my free variable. So remember, the book will have S1, S1, S1 for x4. I don't really care what you do. If you use S1 or x4, it's fine with me. I'm fine with either, okay? So we want integer values, okay? We want to balance this equation. It doesn't make sense to have 1/4 of a molecule of potassium superoxide, right? It doesn't make sense to have 1/5 of a molecule of carbon dioxide. It doesn't work that way. Either you have a whole molecule or you don't. We cannot have a fractional amount of molecules because molecules are made up of atoms, and atoms are the smallest spaces that we have for this intents purposes, right? Not including quarks and leptons and things like that. So I need full number of molecules, okay? So since my application solution deserves a whole number amount, we are going to choose x4 to be 3 because that will clear all of these denominators and I'll have a integer value amount of my molecules and compounds. So I can say that x1 is 4, x2 is 2, and x3 is 2. Since this fourth one doesn't make sense as a part, right? I don't need it. I only need 3 coefficients. So my x4 is 3, okay? My x3 is 2, my x2 is 2, and my x1 is 4. Okay, so remember, this is the free variable amount. This can be any number. Any number I have here will change the values I have here, but it's nice to have them be whole numbers. I also don't want to say, we also use the lowest value. Okay, so what I mean by that, I wouldn't want to choose 6 for x4. I don't want to have 6 and 4 and 4 and 8. Okay, when you balance an equation, you use the lowest integer amount needed for your balancing. Okay, hope that was helpful. Let's do another example. Okay, I believe this is our second to last example. We have 2 more or 1 more after this. So the average volume of traffic in a few intersections per red light is given. Okay, there's a diagram that goes with this as well. I'll show you in a second. Find all the possible values for x1, x2, and x3, and we want to know what is the minimum volume of traffic from C to A. Okay, so the arrow gives you the direction of traffic, right? Each of these nodes is a stoplight. So when you come to this stoplight, you can go forward or you can make a left turn. Okay, when you come to this stoplight, you can only make there's an arrow here, so you can go straight or you can make a left, but there's no right turns, right? If you're coming down this road and you make an intersection, you can either go left or you can go right, right? If you're going this way at the stoplight from B to C, you can make a right turn, and that's it. You're hitting a one-way street. Okay. If you are going this way and you come to this stoplight, you can go left to this road, or you can go straight, right? That's how we're reading at this. We're taking this traffic map and we're condensing it down and taking out all the nonsense. And then we also have, so our arrows are the flows, but they also tell us sort of our options, right? Now the option that we have at each stoplight is helpful, but it's not super necessary. So we have traffic flow from B to C, from C to A, and from A to B. So what we're going to do here, we're interested in the minimum amount of traffic from C to A. So we want to know what's the smallest value X4 can be, right? We're not going to be able to figure that out until we're done solving all of these values for X1, X2, X3, X4. Okay. So this is the average volume. So on average, from a green to a red, 50 cars go through this intersection. Some of them go straight, 25 of them go this way on average. Okay. All right. So then that might help us know that on average it might be 25 here. But that might not be the case because we have these other values as well, right? So that's an assumption right now. So that's how we're going to look at it. Okay. So if I'm looking at X1, okay, what is X1 going to equal? It might be easier to do this by node rather than looking at X1 and saying, hey, there's, things coming in and things going out. So by node, we can talk about this. For A, I have 40 in, 30 in, X4 in. So those are all the things that are coming in. So I basically have 70 plus X4, and going out, I have 50 plus X1. And those two things have to equal. Everything that's coming into A has to be the same things that are going out of A, right? If these people are going through the stoplight, they're either going to go this way or that way. So all these people coming in, it's 50 plus this amount. Okay, same thing with these people coming in, right? So 40 plus the 30 has to equal what's going to be coming out of this intersection. Oops, that's out also. Okay, so all the things coming in, 30, 40 plus X4 has to equal the things going out, 50 plus X1. Okay, and we're going to do that with each node. Okay, because that's what happens when you go through a light, right? You go in, you have to go through a light, you don't sit in the middle of the street. So we're going to do that with each node. So that was A. Okay, it's the same as the amount going out of an intersection. So A is the 40 plus 30 plus X4, and going out is the X1 plus 50, right? 40, 30, X4 in, 50, X1 out. For B, X3 in. So you might want to pause this so you can write your own equations and then see if it matches up with what I'm going to do in the rest of the video. But B going in, it's X3 in, X1 in, 25 in. Out is X2, 40, 55. Okay. X1, X3, 25 in, 25, 40, X2 out. Okay. X2 out, 40 out, and that's the only ones for B. X2, 40, and where's the 55? Oh, 55 out also. C is the same thing. In is 50. In is X2. Out is 25. Out is X4. So 50 plus X2 has to equal 24 plus 25. Okay. So turning this into our augmented matrix. Again, before we even turn this into an augmented matrix, we need to put all of our variables on one side and all of our values on the other side. So that gives me this equation as a minus X1 plus X4. This and this adds up to negative 20. Now obviously I could reverse these things, so it's a positive 20 and these are negative. It doesn't matter, right? This one gives me X1 minus X2 plus X3 is 70. And same thing here. x2 minus x4 is negative 25. Okay. Now again, it just matters which side. If I had put everything on the other side, if I made this 25 and subtracted the x2, that's just like taking this equation and multiplying it by negative 1, which is one of the things we're allowed to do in our elementary row operations, right? So it doesn't matter how you do it. It doesn't matter if you like the negatives or not. You can switch some stuff around real quick if you want to. I'm saying as far as the negatives go, if you don't like it, before you put it in the matrix. But it'll all get taken care of when you do your Gauss-Jordan elimination. So when we put this into an augmented matrix, these are my x1 coefficients, my x2 coefficients, my x3, and my x4. And then my right hand side. Okay. Again, lots of things we could do. I can multiply this by negative 1. So I have a 1 here. I can just swap these rows because that's easy to do too. But my goal is to get a 1, zeros, come to the next row, which would most likely be here, get a 1, zeros, etc. If you notice again, 3 equations, 4 variables, there will be a free variable, right? So if I wave my hand and do some magic, put this into reduced row echelon form, again, you should do this on your own to make sure that you come out with what I get, right? So it's a good way to check your work to make sure you're doing the right things. But this is the values that you're going to get, okay? And as you notice, there is a free variable here, okay? x4 is a free variable. x3 is 25. x2 is negative 25 plus x4, that free variable. And x1 is 20 plus x4, right? Therefore, x4 is free. x1 is 20. Move the free variable to the other side because I'm trying to solve x1. x2 is negative 25 plus the free variable. And x3 is 25. Okay, so now that I have my values, remember my goal, my end result, was to minimize the traffic from C to A. I want to minimize the value of x4. What's the smallest value that this can be, okay, for our situation? Okay, so we want to minimize x4 in order to minimize the traffic from C to A. So let's just look at x4, right? x4 doesn't come up in the x3 value because it's just 25, but I have 2 equations that it does pop up on. 20 plus, this should be 20 plus x4, not minus x4, apologies, and x4 minus 25, okay? So these are the 2 values that I have. This should be a plus. I'll fix this in the write-up. So if I look at what's the smallest thing I can have, right? So remember, this has to be, we're talking about traffic. This has to be a positive value, right? It has to be positive. I can't have a negative value. So I'm restricted in the values that I'm allowed to have. So if this is, if this is positive, right? This isn't really going to help me out, right? Because I'm adding here. So this can just grow without bounds, okay? However, this does put a limit on how high I can be, right? The largest this value can be is going to be 25, because once x4 is more than 25, I'm going to start to have, I can't be less than 25, because if I'm less than 25 here, right, if I'm less than 25, I'm going to have a negative value for x2. So the smallest value I can be for x4 is 25, because then that means I got 0 values, 0 number of cars going through x2. And again, you might be like, well, what about 20? Again, remember, I messed up, okay, so this should be a plus. Just imagine that in your mind right now. You'll be okay. So this is what allows me to minimize. Okay, so the smallest value I can be is 25, because if I'm any smaller, that makes this negative, and that's not okay. Okay, so therefore the minimum value of traffic from C to A is going to be 25 cars, right? So this is the minimizing equation. The other one, since it's positive, it doesn't help me to get the minimum, right? Because if I did choose 0 here, I would have negative 25 cars, right? That's not going to work, right? So our last example. So we are going to do clearing denominators, partial fraction decomposition. So this shows up semi-often in like an Algebra 2 class. It gets used in calculus a little bit, and you will definitely see it in differential equations when you're doing Laplace transforms. Basically, it's a way for you to take a rational equation and decompose it into its components. Okay, I actually use this method a lot when I teach algebra, when I'm trying to come up with a neat problem, right? If I have a problem where I want students to add two rational functions together or simplify a rational expression, and I don't want it to get all messy, I have to use partial fraction decomposition in order to create the problem, right? So I'll start with the end result that I want. Maybe I want them to cancel stuff really well, and then I will use this method to create the problem that I want them to solve. Okay, so that's how I use this. I actually use this method very often, but it is something that also pops up in differential equations and a typical algebra class. So let's get into it. Okay, so we want to find the missing values in the following partial fraction decomposition. So basically, I have this expression, and I want to break it up into parts so that I have some value over one of the factors plus another value over the other factor, so that if I were to add them together, I would get this. That's how I think about this. Okay, I generally start with, this is the problem that I want to give students, but maybe this is the answer that I want. Okay, so then what values do I need for A and B for this to be their answer? Okay, so again, that's how I think about it in my usage of partial fraction decomposition, but there's lots and lots of uses of partial frac decomp that you'll see in other classes as well. So generally, when we have an equal sign, and some fractions, because that's all they are, right? This is a number, this is a number over a number, right? If I chose x is 10, this turns into 11, this turns into 9, this turns into 99, right? And then this turns into, 29, or what have you. So these are values. This is a fraction, this is a fraction, this is a fraction. How do I add fractions together? I make common denominators, okay? Now, when I have an equal sign, what I'm allowed to do is I'm allowed to clear fractions. I find the common denominator, and I multiply the entire equation by the common denominator, and then things cancel out, okay? Some of you are probably great at this. If you ever had me before, we do that a lot in my algebra courses. So it's the same thing. We want to clear these denominators, right? The LCM here is x minus 1, x plus 1. So I multiply this by that, and I multiply this by this value as well. Things will cancel out, and you'll be left with this, right? When I multiply this value on this side, this denominator cancels with the LCM. When I multiply it on this side, the x minus 1 cancels, but the x plus 1 stays times a. When I multiply it times the other term, the x plus 1's cancel, but the x minus 1 stays. Okay. Now from here, what I'm going to do is I'm going to distribute my a, and I'm going to distribute my b. Right? Oops. Okay. So I distribute to simplify things out. Now, from here, I don't have anything else to do as far as simplification. Okay. But what I do want to do, there's a couple ways to think about this, but I want to make some equivalencies. A and B, A and negative B, I should say, are constants. The only constants on the the left-hand side is negative 1. So that means if I take this constant value and add it to this constant value, I need to get negative 1. The only values that are x's on this side are ax plus bx. That has to equal 3. So a minus b has to be negative 1. A plus b has to be 3. Okay, there's no other way for this to work. So the left and right hand side equivalencies, they give us the following. 3x is ax plus bx. -1 is a minus b. This leads me into an equation. This is my coefficients. These are my coefficients. These are my coefficients. Right? If I were to take this and divide this entire equation by x, I would have 3 is a plus b. I don't actually need this x. I'm just doing that to show the equivalencies from the left hand side and the right hand side. Okay? But this x is actually arbitrary. I don't actually need that. This is just to show you where the equalities come from, where the equations are made from. Okay? So 3 is the same as a plus b. -1 is a minus b. And I can throw this into an augmented matrix very easily. Okay? Now again, my goal is to put this into reduced row echelon form. Okay? So I will subtract these two in order to get rid of this equation. So R2 becomes R2 minus R1. Okay. And then my backwards phase is that R1 becomes R1 plus R2, because then they'll have opposite signs and they can 0. Oh, I guess I can subtract this by -1/2 since they're both constants. Okay, apologies. Then now I can 0 out the value above it. Okay, I was getting ahead of myself a little bit. And these are my values. So that means that A, because this is the A's first, right? This is the A's column, the B's column. A is 1, B is 2. Okay. So if I gave this problem to a student, this would be their answer. Right? So that's partial fraction decomposition. And that is our last example. Okay. Hope you enjoy this. So obviously these are not the only applications, right? When you go through a regular algebra class, you have lots of different applications for systems of equations. They're all pretty dumb. They're things like if you set up a stand that sells hot dogs and hamburgers and you sell 20 hot dogs for $2 each and 30 hamburgers for $1 each, and at the end of the day you have $130. How many hot dogs did you sell? How many hamburgers did you sell? Right? They're very, very arbitrary, but again, we're moving away from very simplified examples to more applicable examples to your field of study. Okay? So, I'll see you guys on the next video.